Okay, so let's talk neurotransmitters. As I mentioned yesterday, we'll just kind of pick up where we left off. It's important to understand neurofunction. Right, that's kind of the first part of the chapter is neurofunction. So let's just look back at the process. Now, this is a little like chaotic to look at, to be honest with you. So here's what I want you to kind of visualize and imagine. Each one of these neuropathways is a chain of neurons that are all connected together. And so if you visualize it, it makes a little bit more sense. So this is like an MRI scan, and they just highlighted digitally where the neurons are. So on the left, we have the serotonin pathway in the brain. So this is a connection of thousands or hundreds of thousands of neurons that are all connected together in this big link, right? So this is the serotonin pathway in the brain. It occupies much of the midbrain, right? The monkey brain, as we call it, the limbic system, the mammal brain. You can see it's very specifically shaped. It runs through the brain stem. It has various access points in the brain stem because that's your sensory information. And obviously your brain has to communicate through your body, through the spine, right? So this is the serotonin pathway. We'll get more into serotonin in a second. This is the dopamine pathway. The dopamine pathway doesn't take up as much real estate as the serotonin pathway, but this is a very significant part of your emotional well-being. Right? There's really two types of dopamine that we'll talk about today. There's the anticipation dopamine, and that's like I'm excited to do X, Y, or Z. And then there's the reward dopamine, and that's the one that everybody thinks about. That's the one where it's like, oh, I ate this sandwich and it was delicious, or sexual gratification, and then you get this dopamine release in your brain. And the whole idea is that hopefully it will incentivize you to participate in that activity again, right? So, but the reason why I'm showing you this to start off, I want you to visualize, because we started at the neuro level, right? And we're going to really hone in on neurotransmitters today. So you have to just kind of comprehend the big picture here. That one neuron is a part of a nerve, and all of these nerves are linked together in an entire network of communication. So imagine that this is either firing or it is not. If the neuro network for serotonin is firing in a circuit, let's call it a circuit, if the neuro circuit is firing, we have serotonin production, and you're feeling good. You're feeling normal, relaxed, calm, maybe even happy, maybe even elated, maybe even so much serotonin so many times that you're in a state of mania, cloud nine. You just found out you got into your school, we scan your brain, and this network is lit up. So that's what I want you to imagine. These are neural pathways. They are a connection of neurons. Neurons are the smallest unit. The pathway is the biggest unit. So when we talk about neurotransmitters today, we're going to talk about the actual molecules that are produced and released and received. So remember, the term I used yesterday is electrochemical. There's two parts to brain communication. You need what's called an action potential, right? Vocab word for electrical charge. And that's what we just talked about, like the neurons can either be resting or they can be firing. And what happens when they're firing is the ions that enter into these receptor sites change the polarization, and now they have a charge. And when you have a charge, it has to be discharged. So we say the neuron fires or has an impulse. Really, the neurological term is an action potential. An action potential is when a resting neuron fires. So you weren't thinking about something, and then you were, inside. So that neural pathway just fired for whatever reason. Something made you think of it. Priming maybe, I don't know. So neurons are either resting or they're firing. And after they expel their contents, the molecules that they produce, they have to get back to their normal resting state. That's what's known as a refractory period. It is the very brief period after a neuron has released its contents when it's trying to restabilize itself in terms of a charge. So when a neuron fires, then it has to get back to this refractory period before it can fire again. So after a neuron releases its molecules, so the molecules are what we're going to talk about today, it reabsorbs them for future use, right? So we talked about depression yesterday and the serotonic system. So here's your serotonic pathway right there. So if serotonin is not being produced at a high enough level, then your mood is not going to be what it needs to be, right? So let's say maybe it's because your brain doesn't produce enough serotonin. bless you. Or maybe your brain doesn't release enough serotonin. And for whatever reason, serotonin is being released and not activating receptors, or enough of it is not being released. So we talked about the difference between agonists and antagonists. All of those are foreign substances, by the way. An agonist or an antagonist is a term for a chemical that originates outside the body and somehow gets into the bloodstream and affects the brain. It's a chemical that starts outside the body. Like, for instance, a virus, right, can get into the bloodstream. It can affect the brain. Caffeine is one of those 4% of known substances that will penetrate the blood-brain barrier, meaning it will go from the bloodstream of what's in your arteries into the synapses of the brain. Most molecules are not small enough, or let's say chemically, structurally pure enough to get into the brain. So if you eat something or you take a pill, right, you have a headache, and you take aspirin, acetaminophen, which is Tylenol, then what happens is it's metabolized into your stomach, it gets into the bloodstream. When that blood with the acetaminophen in it gets into your temporal artery, it leaks out into the synapses of the brain, and it starts landing on receptor sites and causing brain activity, in this case blocking brain activity, right? So if you introduce a chemical into the brain and it mimics a molecule that your brain produces, that's what's known as an agonist, right? So it's a synthetic chemical that's so close to a brain molecule that will actually stimulate the brain. So the example we gave is serotonin. There is a synthetic form of serotonin, and it's not legal for you to buy or take. What is a synthetic form of serotonin? Ecstasy, MDMA. So ecstasy is pharmaceutical grade serotonin. It's been created in a lab. It's a chemical compound. It's put into a pill just like a lot of drugs. So you take it, absorb it into your gut, where most of your serotonin can be absorbed anyway. It gets into your brain and massively floods your brain with serotonin, right? The problem with that is if we have an agonist, something that mimics a brain molecule, your brain doesn't understand foreign substances. It only understands natural substances. So when your brain is flooded with artificial serotonin, I don't want to use this word, but for all intents and purposes, it believes that we have an oversupply of serotonin. So when your brain is flooded with an artificial supply of serotonin, what does the brain do? It produces less serotonin. So if you were to take someone who suffers from clinical depression, meaning they have lower levels of serotonin, and medicate them with ecstasy, it would work in the short term, but actually would make it worse in the long term, because the brain would stop producing the minimal levels of serotonin that it has. So sometimes agonists are not the answer. Sometimes antagonists are the answer. And antagonists are different. If agonists mimic, antagonists block, like anti, to prevent, to stop. Antagonists block. So sometimes we can get a chemical into the bloodstream and it gets into the brain, and instead of activating a receptor site, it blocks that receptor site, right? Like a door or a gate prevents molecules from getting in there, right? So in the case of antidepressants, it doesn't actually block the receptor site, it blocks the sending site. It blocks the reuptake or the reabsorption of serotonin. So after that serotonin neuron fires, releases the serotonin molecules into the synapse, it reabsorbs them again so it can go back to resting and save them for later. So imagine the analogy if you have like 1,000 ping pong balls, right? Or let's say 100,000 ping pong balls, right? So let's say the normal human brain has 100,000 ping pong balls. And that's what makes you feel normal. You release 100,000 ping pong balls, they hit 100,000 receptor sites, everything is good. Well, let's say the depressed brain only creates 1,000 ping pong balls. Well, if we can't introduce 99,000 more, we can at least block the reabsorption of those balls. So now you get 1,000 ping pong balls that stay in the synapse longer, they bounce around longer, and it's more likely that they will not only activate 1 time, 2 times, 10 times, 100 times. So 1,000 ping pong balls landing in the receptor site 1,000 times or 100 times is the same level of serotonin. I know that's a stupid metaphor. Okay, it's a dumb metaphor, right? But the end result is the same. And what I mean by that is 100,000 receptor sites have been activated. Either way, right? So it's the same result. So antagonists block, agonists mimic. And the problem with agonists is they tend to be addictive. And what makes a chemical addictive is because your brain stops producing the natural, so now it's going to crave the synthetic, right? So you have to wean yourself off, right, instead of just quitting cold turkey. All right, so that's the difference between an agonist and an antagonist. Now, here's the other problem. It's not just serotonin. It's not just things like antidepressants. You have things like Adderall. That's an agonist for dopamine. Uh-oh. So what happens when you abuse Adderall? Well, you're introducing, let's say, flooding your brain with artificial dopamine. Oh no. And not only that, you're stripping out the brain's ability to activate and receive the dopamine that it has. So if you abuse Adderall, meaning you're taking a dopamine agonist, which is an amphetamine, that you don't need to take because chemically your brain produces enough dopamine, so you're flooding your brain with artificial dopamine, which means your brain is going to what? Stop producing dopamine. That's a problem. That's a huge problem. So don't snort Adderall, ladies and gentlemen. You guys laugh. Don't do it. It's not good. It's not good, right? That's the number one abused drug on college campuses, and there's a lot of research that are connecting Adderall to a massive spike in college-aged suicides, right? So again, that's still in the early phases of research, but you do not want to manipulate your dopamine levels in your brain because you need dopamine to feel well, you need dopamine to be motivated, you need dopamine to just manage and balance your emotions, so you don't need to artificially stimulate your motivation, right? So that's agonist versus antagonist. That's a basic concept that you have to visualize or understand in your brain for us to move on to the molecules themselves. So now that we know the process, one neuron releasing molecules received by another neuron causing action, let's talk about the molecules themselves. So there's 8 of them. We're going to just put like headings. And I try to come up with cute little like titles for each of them, like they're characters in a movie, right? So remember, these are all pathways. They're different pathways in the brain. One pathway is just dopamine. It's a link in the dopamine chain. And there's actually several dopamine pathways inside of this one. There's like 4 different ones. But anyway, for all intents and purposes, dopamine, neurons create dopamine. They release dopamine. They absorb dopamine. They reuptake dopamine. No other neurons are involved. So there's specific neurons for specific functions. You have memories, you have thoughts, you have emotions. All these things are different pathways in your brain. They're either activated, which means action potential, or they're resting. Right? You're not thinking about the lyrics to a certain song because that pathway in your brain is resting right now. And then it just popped into your head. Ha ha, now it's activated. Right? So pathways in your brain, they're either resting or they have the potential to fire, which is action potential. So let's start with the first one. I probably put more information than you need on each of these chemicals, so I don't know that you want to write as much as I'm going to explain, right? But the first 2 I decided to start with are actually not technically neurotransmitters. They're gliotransmitters, they're like amino acids, right? So I started with these 2 for a reason. Okay, let's start with glutamate. Glutamate is released by one neuron in its way to communicate with other neurons, and glutamate is a molecule that enables neurons to fire. It's what actually activates a neuron. It stimulates action potentials, if you will. So glutamate is different than, say, a serotonin, dopamine, oxytocin, norepinephrine, endorphins, right? Adenosine, because glutamate is what makes the process work. Glutamate is what stimulates, the word is excites, neurons. So the more glutamate you have flowing through your brain, the more neural pathways you activate, the more your mind starts racing. So if you're laying in bed at night and you have 1,000 thoughts running through your mind and you can't relax or calm your mind, there's probably way too much glutamate concentrated in the fluid of your brain. So glutamate is an amino. It's a gliotransmitter. It's an amino acid. Now remember, what you eat has a big impact on your brain health because we talked about gray matter and white matter. The gray matter is the cell bodies, right? We learned the Latin term for cell body. You learned the magical medical term. What is the magical medical term for body? It starts with an S. Soma. Soma means body. Soma means body. So neurons have cell bodies. That's where the nucleus is. you see things like the somatosensory cortex. Oh, well, soma, sensory. So what is of the 5 senses, which one has receptors on the whole body and not just the eyeballs or ears? The sense of touch. So the somatosensory cortex is where you process the sense of touch, feel, right? The reason I'm telling you this is that the strategy for this chapter is no different than any anatomy or any biology. You don't want to memorize terms outside of their context. So in other words, learn what they mean so you can figure out the answer. So if you're stuck between somatosensory cortex in the brain, and you're like, ugh, it's either A, vision, or E, touch. Which one is it? Well, I know soma means body, and your arms can't see stuff, so it's got to be touch, right? Like, that's the strategy. The strategy is learn a basic level of vocabulary for anatomy, and it will help you figure out the right answer, right? And you learn things like soma means body. Does anybody remember what the word cortex means? It's not the inner, but the outer. It's the surface. The cortex is the surface. So when we say the somatosensory cortex, it's the surface of the brain that processes touch, processes the sense incoming from the body, right? There's also a somatic nervous system we'll talk about tomorrow. Well, that's the nerves of the body. So it's like muscular nerves, pain receptors, movement, motor and sensory. So again, somatic nervous system versus autonomic. I don't remember the chart from the board. I'm freaking out. No, the word soma means body, and you know that, and so you're going to figure out the right answer. So there's a basic level of just anatomy, and there's a basic level of things that you just need to know. So one of those is gray matter versus white matter. And the gray matter is the surface tissue of the brain. That's where the cell bodies are. That's where the dendrites are. The white matter are the axon cables, and they're encased by myelin or myelinated sheath, and the myelin and the axon cables are held together by glial cells. And the glial cell attaches the axon cables together, but it also brings them nourishment. Very important function of glial cells. Taking nutrition out of your food and nourishing your neurons. So you eat something like, I don't know, cashews, right? It's got good fatty acids. Or you eat amino acids or omega-3 fatty acids, fish oils, you eat fish, right? Especially like deep water, white flaky fish. You get these fish amino fatty acids into your bloodstream, and what happens is they leak out into your brain from the temporal artery, and they help to nourish the glial cells around your neurons. So you need good nutrition and good calories to feed your brain. And remember, if you don't feed your brain, it dies. There are pathways in your brain that you don't use, so they're not getting nutrition. Like you don't learn to play the violin by a certain age, that pathway dies, and the brain absorbs it. Glial cells help to metabolize the dead tissue, and then you no longer have access to that. So if you want to learn to play the violin at 17, it's going to take you a heck of a lot longer, right? Because we have critical periods for those things while you still have access to the pathway. Same thing is true with language. You want to learn a second, third, fourth, eighth language, you better do it before the age of 5, because once you don't bring nutrition, blood flow, fatty acids, amino acids, nutrition to those neurons, they die. They atrophy, right? So glial cells are key in nutrition. They bring the nourishment from your bloodstream to the neurons. So you eat good foods, and those lipids get into your brain, and they feed the glial content, right? So the reason why I'm telling you that is glutamate and GABA are great examples of this. They can be impacted by your diet, right? So they can get into the glial cells, they can cause all of the neurons around you to start firing. So glutamate is the excitatory neurotransmitter. It's really a gliotransmitter because it's like coming from the white matter, not so much being released in the synapse. So I'm calling it the activator, right? The activator is glutamate. Now think about gluten. Gluten is a preservative that's been created in a lab that's very close to glutamate in the brain, and what it does is preserves things that go bad, right? The downside to this, especially certain forms of gluten, like monosodium gluten or MSG, right? It does a really good job of preserving Doritos so they don't go bad. The downside is MSG is one of the 2 types of gluten. There's bound gluten, meaning it's stuck, it can't get through the blood-brain barrier, and those are things like proteins, red meat, right? Those things get stuck in the bloodstream, but they never affect the brain. That's not bad gluten. But you also have free gluten, and that's in your bread products. That's a preservative that's been created chemically in a lab to preserve your food. But the downside to that is it can also get into your brain. So the more gluten that you eat, the more free gluten that you eat, the more glutamate concentration you have in your brain, and it activates neuro messages. So you can eat enough Doritos to have a panic attack, right? Because so many neurons are firing for so long, it causes levels of stress. Migraines can be gluten-induced. It's a good place to start if you suffer from migraines. You can cut out gluten from your diet, see if it helps, because the whole idea is a balance between glutamate, which stimulates the neurons, and GABA. Whoops, wrong direction. GABA. GABA is what counteracts glutamate, right? So these are different because they are more amino acids, neurotransmitters, and they're not so much like dopamine, serotonin. Yes?
Might be unrelated, but wasn't like the downside with MSG like shown to be like a racist study? Like it wasn't actually like true?
Oh, well, it may have been biased, like if they had an unbiased sample. But no, MSG has been tested several times in labs. And yes, the study that you're referring to was like, because MSG is used often in like soy sauces and sodium-based preservatives that are used in like Southeastern Asian cuisine. And so they thought maybe it was like an anti-Asian sentiment situation. But no, MSG is monosodium glutamate. It's in like Doritos and stuff like that. And you can talk to medical professionals and they'll corroborate this. But no, there are clinical trials, double-blind studies that are peer-reviewed that have shown significant evidence that MSG is I don't want to say bad for your brain, will spike. It acts, what it is an agonist for glutamate. So it will cause neuroactivity. Now, here's the real question. How much would you have to consume? I don't know. But it can build up over time. So yes, I don't say you go home and eat 6 Doritos and then you have a migraine, right? But if you sat down and you ate a whole family-sized bag of Doritos and nothing else, you might feel anxious until your body can metabolize all of that and get it out. Now remember, everything that you take, eat, snort, ingest, everything that you get in your bloodstream is only there till it can be metabolized. Same is true of medication, right? So it's not permanent. Most even drug-induced toxins are not permanent. Now, there are some caveats to that, and we'll talk about this, right, much later on. But like when we get to dopamine, right, there are things that are safe to take for some brains and not safe to take for other brains. So I get this question a lot, and it's a loaded question like, Coach, is it safe for us to be smoking marijuana? What's your opinion on that? Well, no, absolutely not. It's massively damaging the brain chemistry that your body is fighting very hard to balance and could be irreparable, right? But if you were 25, it's not a popular opinion. Your parents probably wouldn't love hearing me say this, but medically speaking, you could probably wake and bake at 25 and not have any. Now, it'll affect you while it's in your system, but the developed prefrontal cortex, the dopamine receptors. Now, there is a level of dopamine flooding that you can do that will deplete your dopamine pathways in the brain, but it's much more likely in higher concentrations at a younger age. Yes?
What do you think about like the doctors that are super lenient on prescribing Adderall to 8-year-olds?
Yeah, I'm not a fan of Adderall. In fact, I'll be honest with you, and I'm not a medical professional, so let me give you a caveat. I heard this from an unnamed medical professional that told me they would not be surprised that if in the next 20 years Adderall was banned by the FDA. Adderall is horrible for a developing brain. And the reason why is it's an amphetamine, baby meth. Okay, and what Adderall does is stimulates motivation for hyperactive brains by increasing the dopamine levels. So my personal opinion, I'm not a medical professional, I'm not a scientist, but I can give you my opinion on it. I'm not a fan. I'm not a fan of children taking Adderall. And if they do take it, I would hope that the plan would be in short term, in small dosages. But that's just my opinion. I'm just giving you my opinion on that. Don't take that as gospel. I know people take it, and I know it helps them. It benefits them. Again, Xanax works, you don't need to take it. Adderall works, you probably don't need to take it. Right? So the whole idea, again, it's a fair question. It's not yes or no, it's how much for how long and in what situations. Right? Can I imagine all or nothing, like never a scenario where a child with hyperactivity disorders in their brain should ever take an amphetamine? Well, no, I'm not saying never, Or let's say how much, how often, in what situations, and for how long. Should it be as prescribed as it is? In my opinion, no. Should it be prescribed in people like 8-year-olds? In my opinion, no. Because your brain is balancing. They're prepubescent. They haven't even gone through the chemical changes of puberty yet. The brain is learning chemical balance. Yes? Did you have a question? Okay. So, but that's my opinion. I mean, again, that's purely an opinion. I'm not going to state that that's a medical fact. You can think for yourself on that. I'm just going to tell you my thoughts as a parent and somebody who studies psychology. I'm not a fan. Right? And I'll tell you why when we get to dopamine. So GABA is the counteractor to glutamate. Right? So if glutamate stimulates neurons to fire, GABA is what calms them back down and helps them rest again. So if you can increase the GABA in the brain, you can counteract the effects of glutamate. So I stole this illegally, probably copyrighted offline, right? This picture. And I like it because it shows this diagram of a glial cell, which is bringing nutrition to 2 different neurons. So this is a GABA neuron, this is a glutamate neuron, and they're both connected to another neuron. So glutamate is going to stimulate this neuron to fire. Let's say it's serotonin or dopamine. GABA is going to cause it to stop. So what we want is a counteracting balance. The neuron fires, the neuron relaxes. The neuron fires, the neuron relaxes. It doesn't overfire, it doesn't over-relax. Because the thing is, if you don't have let's say you can increase the GABA in your brain and you relax neurofunction. The problem with that is you can't just relax stress function in the brain, emotional function in the brain. You're lowering all neurofunction in the brain. In other words, you can't isolate the dopamine pathway or the serotonin pathway. It's just GABA or less GABA. So you're also lowering neurofunction for thoughts and emotions and problem solving and insight and creativity. So you would be in like a brain fog. So you want to balance, right? So I, again, illegally stole this. It says glutamate and GABA. Optimal is a balance of the 2, because then when neurons need to fire, they can. But then when they don't need to fire, they can rest. If you have too much glutamate, anxiety, possible seizures in extreme cases, right? So that's GABA and glutamate. The activator is glutamate. The silencer is GABA. Now let's get into more of your traditional neurotransmitters. I wanted to start with those because they kind of cause the neurons to fire or prevent them from firing. So now let's get into the neurotransmitters that are being fired, right? So the first one is serotonin. Serotonin is a good one to start with because this is a famous one. I'm going to call this one the mood molecule. I don't want to call it the happy molecule because then it'll make you think of something else. And also the problem is that your level of serotonin may not necessarily make you happy, might help you feel just well, normal, melancholy. Like you're relaxed, you're calm, you're feeling good, you're feeling okay, but you're not elated, you're not manic. Like you find out you get into college, serotonin levels are going to spike, and you're going to feel elated, right? Your dog dies, you have to put the dog down, serotonin production is going to stop for a while, you're going to feel sad. That's normal, healthy, emotional function. So the clinical depression is not you being sad. Clinical depression is a lack of serotonin production that's not related to a trigger, right? So you feel sad, apathetic, and it's prolonged for 2 weeks or more. That's more likely a sign of clinical depression. But if it happens one time, for a whole month you're depressed, after a family member passes away, that's perfectly functional human behavior. Now you eventually have to hopefully get back to some normalcy. But I don't want you to connect lack of serotonin with depression. I feel depressed right now is not an accurate statement. You feel sad. One does not feel depressed. One either has depression or one does not, right? And so you can fluctuate through bouts of depression. But depression is not a feeling. Depression is a disordered level of chemical imbalance. That's why when we try to use logic, when people have depression, it doesn't connect. It's not logical. It's not related to rational thinking. It's based on a chemical imbalance in the brain. And that's why it's one of the 2 known psychological disorders that can be completely genetic. It's depression and schizophrenia. Everything else is culturally or environmentally induced. Yes, that's right. You cannot be born with anxiety. That's a fallacy. Anxiety is completely nurtured, which is good news. Because if anxiety is nurtured in as a disorder, it can be what? It can be therapeutically nurtured back out. Now, you could make the argument that people gain personality traits from their genome, and some people are genetically more anxious than another person, but as a disorder, a level of disordered anxiety, generalized anxiety, social phobias, social anxiety, agoraphobia, right? Panic disorder, those things are nurtured, right? Those things are environmentally induced. And I don't say that to downplay them because they're very real, but there are two genetic disorders that we know about that have spanned all of time and space and have been throughout all of recorded history where they've noticed emotional disorders, and that's schizophrenia and mood disorders like depression or bipolar, right? So serotonin is effectively regulation of our mood, plays a vital role in neurocommunication, diet, and sleep. Serotonin, interesting fact, is also considered a hormone. Hormones are in the blood, neurotransmitters are in the brain. So because serotonin has, they're learning this. This is new. This is new knowledge that has a lot to do with our gastrointestinal system, your gut. A lot of serotonin is produced, metabolized, whatever. Somehow the gut is involved in serotonin balance. So good digestion equals positive serotonin balance, right? So oversupply of serotonin causes manic episodes, extreme mood swings in the positive. Undersupply is linked to depression, long-term, right? Sadness in the short term. Serotonin disorders include clinical depression, mania, as if you're high or normal. Bipolar would be if you fluctuated mood swings from mania to depression and back up to normal, or mania, depression, mania, right? At bipolar 1. Massive mood swings with spikes of serotonin, then depletions of serotonin, then spikes of serotonin. It's the brain's inability to balance the level of serotonin. So taking antidepressants can help with bipolar 1 also. All right, so let's get into oxytocin. This is everybody's favorite. This one is kind of like oversimplified, right? Because people think about oxytocin as like the bonding hormone, and it is that. It's involved in that process, but it is more complicated than that, right? So for all intents and purposes, let's look at the value or use of oxytocin. So oxytocin is what's known as the cuddle hormone or the bonding chemical, right? And the reason for that is because oxytocin is the chemical that's released in the brain when we make social interactions, physical contact with people, right? Those things stimulate oxytocin. So oxytocin is a major part of human interaction. Human interaction is a biological need, right? It doesn't have to be physical contact, but physical contact that's obviously like respectful, right? Not like somebody punches you in the arm, right? So like wanted bonding physical contact will release oxytocin in the brain, right? So in fact, there have been studies that have shown that people who will give a tight hug to someone for 6 seconds or more, they see an increase in oxytocin in the brain. Petting a dog shows spikes of oxytocin in the brain, both the dog's brain and your brain. That's why you bond with your dog, right? Holding babies can increase oxytocin in the brain. Even lack of contact, even social bonding. You're sitting in a car with somebody and you're talking your way through an emotional crisis and you feel better afterwards, oxytocin is being released in the brain. So it helps us connect with other people. It's a positive experience because we need to connect with other people, right? Social interaction or social bonding is a basic need. It doesn't matter if you look at Maslow. It doesn't matter if you look at any of the other theories for what human basic needs are, like self-actualization theory, self-determination theory, even ones that only have 3 basic need categories. They include human interaction, bonding. You have to connect with other people. It's not a theory. It's not a theory. It's like, oh, well, I hate people. Oh, well, you're a sociopath. Okay, because in literal terms, you have to bond with people. It's a biological need, right? So it doesn't mean that you hate all people. It means that you have a small niche group of people by which you're probably deeply, intimately connected. So oxytocin is the bonding hormone, right? This is like the nerdiest Valentine's Day card you can give somebody. Like this is love, and there's the chemical formula for oxytocin. But oxytocin serves a biological function also. It's a major vital part of the reproductive process in sex, but it's also a major vital part of the birthing process, right? So oxytocin, ironically, has physical symptoms and emotional connection, right? So studies have shown that oxytocin is released at sexual climax, more often in females than males. That's problematic, right? Oxytocin is also shown release and spike in high levels to help aid in contractions during childbirth. In fact, there is a synthetic pharmaceutical created version of oxytocin. There's a bunch of different generic versions as well. It's an agonist for oxytocin, things like Pitocin. So they can like intravenously add an agonist for oxytocin, which will advance contractions, right? And hopefully speed along the birthing process. But there's some benefits to spiking oxytocin levels when you birth a child. It helps mothers what? Bond with their offspring. So you're being like chemically tricked by nature and brain chemistry to connect with your child at the moment that they are born. It's a very magical, unexplainable thing. And you don't even realize it's happening. You will bond with your child. It's just a chemical thing. Now, some don't. It's perfectly normal that happens, what's known as postpartum depression. So if you have depleted oxytocin levels at birth, then you may not immediately bond with the child. And of course, that can cause emotional damage because new mothers feel guilty that they don't bond with their child. But I will tell you this, so we've had 3 children and in 2 different cities, in 2 different hospitals, and in both cases, or both hospital cases, they come around after the birthing process and tell you about all that stuff. And they talk to you about postpartum depression and what are the warning signs and who to talk to if it happens. And it's normal and natural and like everything's a blur, right? Everything's just like new and crazy. And it's a crazy process, right? When you go through the birthing process with another person. So it's not that irrational for you to be thinking, there's no way I'm going through that. That's perfectly normal. You're 16, you're 17. But there may come a time in your life where you will bond with this little human being that just exited your body like an alien, and you will feel this intense connection that's unlike anything else you've ever felt. And that's just the reality of brain chemistry, right? So let's get into ACH. ACH is a motor function molecule. ACH is a somatic molecule, body. ACH is released in the muscle nerve ending. So one motor neuron to the next. ACH is how the brain controls muscular movement in the body, right? Now, there are ACH disorders, yes.
Remember the ACH?
Yes, most of the time that you see this as an option, like on a test, you'll see the abbreviation. Same thing is true with GABA, by the way. You don't need to know, Siri's going to weigh in. You don't need to know what GABA stands for. Like it'll be in all caps, right? They'll spell out the word glutamate, but they will abbreviate GABA. Usually we'll abbreviate ACH, but it's acetylcholine is what it is. Acetylcholine is a molecule that is in the body that extends from nerve endings in muscle tissue, right? So ACH is how the brain helps to control. The brain's motor cortex is the surface of the brain that controls movement in the opposite side of the body. So like your left motor cortex controls everything on your right side, your right motor cortex controls everything on your left side. We'll talk about the nervous systems tomorrow, so don't worry about writing that down. But ACH is the messenger transmitted between neurons in the body for muscular function. So if you have a disproportionate amount of ACH, you can get muscles that seize up, right? Too much ACH causes muscles to seize up, paralysis, right? So we need to decrease or regulate the ACH level so we can get less muscular function. What's known as dyskinesia, which is involuntary muscular movements or spasms that come with things like Parkinson's disease. That can be an ACH malfunction. You have things like paralysis, obviously. Myasthenia gravis is a form of ACH undersupply. The ACH is released by one neuron and can't cause reception on the other neuron. Alzheimer's disease is linked to ACH imbalances. Obviously, multiple sclerosis is an example. So when you see things like muscular problems, muscular dystrophy or MS, things like THC that are in cannabis, because cannabis acts as an agonist for cannabinoids in your brain. Your brain naturally has cannabinoids, and it helps with paralysis, muscular function, relaxation of the body's nerves. So people who have ACH disorders can benefit, right? Because if they have like muscle freezing or paralysis, increased dopamine in the brain can help to relax ACH communication in the body. So anytime you see ACH, it has to do with muscle function, muscle movement, motor control, right? Motor control. So like paralysis or involuntary shakes, right? Endorphins. This is the only one of the 8 that is a vocab word. I don't know why it's the only one that is, but endorphins are your brain's pain fighters. They're the pain blocker, the painkiller of the brain. And here's the thing about that. right? So they are opioids. Opiates is what they are. They're opioids. They're not opiates. Opiates are synthetic opioids. Opioids in the brain are opioid receptors or endorphins. Endorphin is the molecule that blocks pain signals from the body, but it also helps you feel very euphoric, right? So unlike serotonin, which makes you happy, endorphins make you feel elated, relaxed, calm. So like serotonin's like, I feel great today. I'm having a good day. And endorphins are like, look at me float through the air, right? Like there's a huge difference between euphoria, I'm gonna throw this, right? Feelings of euphoria and just feeling good, right? Feeling calm, relaxed. I'm in a happy mood. Euphoria is a higher level of feel good, right? And that's why opiate drugs, which are opioids, tend to be very, very, very addictive, because not only does your brain like the euphoric feeling of being high, it also gets addicted to the endorphin agonists. So the problem with, if you flood the brain with artificial endorphins and your brain stops producing endorphins, now you will feel and perceive a higher level of pain. It's not because you're in more pain, but it's because there's a lot of minor pains and aches that your body has learned to ignore, your brain has learned to ignore. Well, when you take a painkiller, all of that goes away. You don't feel pain in your body anymore. No aches, no pains, no inflammation. I mean, the inflammation's there, but you don't feel it. You don't detect it. So you feel painless. Well, when your brain stops producing endorphins, you now become very consciously aware of all of your pain, all of your aches, all of the little dull things that you might have been ignoring before. So there's multiple ways to increase your endorphins without taking painkillers. And if they give you painkillers or opioids after a surgery, take them as directed. 10 milligrams means 10 milligrams. Because it's not just a matter of making the pain messages stop. It's also over flooding your brain with endorphins so that your brain doesn't stop producing endorphins. And that's how massive amounts of people in America get addicted to opiates. This is the #1 climbing addiction in America. It's not even close. Most drug-related overdoses in the United States in 2021 are related to opiates, right? Especially an alarming increase in things like fentanyl, right? Or morphine derivatives. So endorphins will block pain and help you feel great, right? That's what they do. Norepinephrine. Now this is one that's hard to say, and a lot of people confuse what it is, but I'll give you a good example to help remember it. So think about like antidepressants. What do? They block the reuptake of serotonin. They are SSRIs. Well, what does Xanax do? It's an SNRI. SNRI is a selective norepinephrine reuptake inhibitor, right? So balanced levels of norepinephrine will help keep you in a regulated level of fight or flight, right? Which is sympathetic nervous arousal. You have a sympathetic nervous system, and that's what gets activated by the amygdala, and that's when you have to fight or you have to flee, right? So you're about to be attacked, you get sympathetic nervous arousal. Adrenaline, cortisol, right? So less cognition, more blood flow, more oxygen, more perspiration, less digestion, right? Your pupils constrict, they don't dilate, right? And your brain is honing in. That's what a stress response is. Now, unfortunately, we do that for tests or something that's not life-threatening and doesn't help you on a test, because you need cognitive function on a test, not fight or flight function on a test. So fight or flight is sympathetic nervous arousal. That's stimulated by norepinephrine. So I called it the fight simulator, right? That's not flight simulator. It's just a dumb dad joke, the fight simulator. Fight stimulator, I should say. So norepinephrine is what triggers a fight or flight response. So if you can take something that will regulate your levels of norepinephrine, then you can keep that stress response from activating, right? It doesn't block cortisol, which is the stress molecule. It helps to maintain a level of normal emotional calm so that you don't simulate fight or flight. Yes?
Is it the same as adrenaline?
Yes, epinephrine is the medical term for adrenaline. Norepinephrine is the brain chemical that triggers epinephrine in the body. So epinephrine is from the adrenal gland. So like if you have an allergic reaction to something and you jab yourself with epinephrine, right, an EpiPen, that's a synthetic pharmaceutical version of the adrenaline in your body. And what it does is changes your blood flow so you don't go through anaphylaxis. Now that's not a cure-all. So let's say you're allergic to bees and you get stung by a bee and you hit yourself with an EpiPen. What's the next step? You need to go to the hospital because that epinephrine is going to wear off, fight or flight's going to wear off, and your breathing is going to become labored and it's going to be a problem. So they need to give you a counteractor, right? Now, the other thing you should always carry with you in your first aid kit, if you're driving on a road trip or hiking in the woods, is something easily over the counter that you can take in case you get bit by a snake or stung by something. What can you take that blocks inflammation? You can take Benadryl. So take baby Benadryl, like children's Benadryl. It's a lower dose. You can give it to anybody, any size human, and chew on it, right? Or swallow it. So Benadryl will help in the short term if you don't have access to epinephrine to prevent you from having allergic reactions until you can get to a doctor and they can give you antihistamines and all that kind of stuff, right? So norepinephrine is the fight or flight. Take something like Xanax, it's an SNRI. Let's move into the next one. This is my favorite. I don't know why, that's a weird thing to say. But dopamine is the most misunderstood molecule in your brain, in my opinion. And the reason why is because of pop psychology. People's interest in dopamine and podcasts and articles have really let's say have really simplified how complex of a chemical dopamine really is. So this is what I decided to call it. Dopamine's character is going to be called the motivator. The motivator. People think of dopamine as the reward chemical. And it is the reward chemical sometimes. But here's why it exists. Dopamine exists in this part of your brain that's known as the mesolimbic pathway. Right? If you want to watch the review video for this chapter, I go into detail using a screenshot from Khan Academy. I talk about the mesolimbic pathway. I talk about dopamine. I talk about the reward prediction error. It's probably, honestly, a little bit of a deviation off course. But you'll learn a lot if you want to watch that section of the Unit 3 review video. But I talk about the reward pathway in the brain, right? What's known as the mesolimbic pathway because it is in the limbic system. It has to do with the prefrontal cortex because you have to be able to make decisions when it comes to dopamine rewards. And you get to make decisions because you have a ventromedial prefrontal cortex, right? And most mammals do not. So your decisions are motivated by outcomes. Most mammals' decisions are motivated by urges and drives. So what does dopamine do? It is one of the most ancient chemicals in your brain from an evolutionary standpoint, which is significant because we have the highest concentration of dopamine on the planet. Weirdly, you look at certain they're doing these studies now. It's kind of crazy. It's kind of interesting. If you Google this and look it up, the raven dopamine studies. Ravens have very high concentrations of dopamine and very complex dopaminergic circuits. It's very strange. Now, some people can be more dopaminergic than others, which means that you probably are more creative. You probably are more of an outside-the-box thinker. You may be a little bit more hyperactive, but you're probably not very organized and you don't tend to get things done. So those are the people that create, beautiful pieces of poetry and art, and they write lots of songs, but they also are highly susceptible to addictions and dying at the age of 27. So that's an issue, right? The Kurt Cobains of the world, Mama Cass of the world, Jimi Hendrix of the world, massive levels of creativity and brain motivation, very, 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 very limited impulse control. Right? So highly dopaminergic people tend to be more creative and less in control of their decisions. Right? And here's why. Dopamine is about maximizing future resources. And let me give you this example I got from the book, and I'll find the author for you, but the book of the theorist that came up with the theory that explains dopamine this way. It's called the reward prediction error. And the reward prediction error is this idea that your brain is going to predict the outcome of behaviors. So I'll just put it all out there. The purpose of dopamine is this, and this is the example that he uses in the book, so I'll give it to you. If you were like a cave person, and you're sitting like crisscross applesauce on the cave floor, you don't have the resources that you need to survive. So the most evolutionary beneficial thing for you to do is to get up out of the safety of your cave, go out into the danger of the world in pursuit of resources. So what causes a person to be motivated to go get up and do? Dopamine does. Because if you sit in this cave, food will not fall in your lap. Water will not trickle down from the ceiling. Reproduction, a sexual partner will not walk in out of nowhere. So in other words, there's a certain amount of action required of us to gain the resources that we need. And the problem is we are wisely skeptical of danger. The amygdala is trying to counteract this dopamine all the time. No, don't do that. That's dangerous. No, don't do that. It looks sharp. That looks hot. That looks spicy. Please don't do that. Can't we just sit here instead? That's the safest way to be. But dopamine says, but it may be awesome. So here's the problem. If this is the last part of your brain to develop, and you have access to maximum amounts of dopamine and minimal amounts of impulse control, that makes you very dangerous beings. 16 to 22-year-old males are the most dangerous beings on the planet. In fact, they exclusively fight our global wars. I wonder why that is. They're highly dopaminergic, highly motivated, highly passionate, and they have a hard time controlling their impulses and urges. Oh, there's very few things more dangerous on this planet than an emotionally charged 19-year-old male. There are very few things more dangerous, and that's a problem. You got to get your way through that so that you can become a more calm, relaxed, but that's a problem. I'm not a very dangerous human anymore, and that's not good for society as a whole, right? Because I'll just sit fat on my couch and let the bad things in my life happen around me, right? I don't go forth and fight wars. So there is a necessary brain development here, but that's what dopamine does. It's very, very, very undervalued in what it does. Most people say, well, it's the reward molecule. Well, it is, but why? So the theory is this, right? It's not just about reward. It's about incentivizing the accumulation of resources. So let's say you go forward and you put yourself out there and you do something dangerous, like stalk an animal, and then you kill it and you cook it and you eat it, and your brain's like, wow, that was awesome. You're much more likely to what? Do that again. So you have two types of dopamine in the pathways of the brain. One is anticipation dopamine. The other is reward dopamine. And you need both of them. Anticipation dopamine makes you excited to try things because they may possibly be rewarding. The downside is sometimes they're not. So you can have anticipation and disappointing lack of reward. Womp, 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 which means you're probably not going to do said thing again, right? So that can work against your evolution. What happens if you really, really build up sexual encounters in your mind and they're disappointing to you? Lack of dopamine means you're probably not going to learn that as a chemically rewarding experience. Well, that's not good for your species. So some things you need to be incentivized to do. Yes. Okay. Question. It can, because you lack motivation. Now, think about this. Let's hit it close to home, shall we? There are things that you can put into your bloodstream that increase the dopamine in your brain, like THC. Stop it. Adderall. Stop it. In fact, they call Adderall baby meth. Why? Because it's an amphetamine. Amphetamines flood the brain with dopamine. And here's the problem. Dopamine works, so let's say you get high on a pretty regular basis. You find yourself the most creative after you get stoned. Well, that's not surprising. Well, here's the problem. You're introducing and flooding your brain with dopamine, which means your brain's going to now do what? Stop producing dopamine. And that means that you now have to continue to increase the synthetic forms of dopamine in your mind, or you won't have enough to get through your day. So you don't have the motivation to get off the couch, you don't have the motivation to go eat, you don't have the motivation to go to work, which can lead to drops in your serotonin level. So lack of motivation leads to sadness, and a lot of times that's a downward spiral into depression. Fantastic question that was. All right, so dopamine is very complex. It is called the molecule of more because it's not just about rewarding you for things, it's also about anticipating an outcome, pursuing that outcome, and if it has a positive effect, you're more likely to desire to do it again, which is how addictions happen, by the way. That's going to be our next score discussion, and we're going to talk about dopamine addictions. And what I mean by that are not cocaine addictions, but like gambling addictions, porn addictions, sex addictions, lying and cheating addictions, stealing addictions. These are all behavioral dopamine addictions, right? Rewarded behaviors that are increasing, and so you constantly have to chase the dopamine from that, right? So that's the reward prediction error, is that if your anticipation is higher than the reward, it's not going to be a situation that you process again, right? Or not a behavior that you're going to do again, right?